Section we're going to talk about laws of inference and what makes an argument valid. What this is about really is the importance of being able to make an argument that actually makes sense, that's actually a valid argument, and being able to determine whether other arguments that other people give are valid as well. So let's start off by defining some terms. We see that an argument is just some assertion that a given statement, which we'll call the conclusion, follows from some other statements that we call the premises. So this is the assertion that a conclusion, which is some particular statement, follows from some set of premises, other statements. Now, not all arguments are valid, right? Certainly you've heard arguments from other people that you think, that's a terrible argument, right? Some arguments are valid and some are not. We say that an argument is valid if and only if the conjunction of all of the premises, so if you join together all of the different premises with and signs, is going to imply that the conclusion is true. All the premises implies the conclusion is also true. And this is a really important part here. This is how we're defining this. So we're saying that an argument is valid if and only if, whenever the premises are all true, the conclusion is also true. So whenever the premises are true, are all true, because it's a conjunction, we need them all to be true, the conclusion is also true. So, I mean, we use this argument all the time, or we use valid arguments all the time. And the most basic one, the most basic example is one that we call modus ponens, which we'll talk about on the next slide here. So modus ponens is an argument that says, if P implies Q is true, and the hypothesis of that conditional statement P is true, then we can conclude Q. And we describe our argument sort of like this. It almost looks like a bunch of, the way they would set up like an addition or multiplication table where you write your statements sort of on top of each other, draw a bar to say this is the end of my premises, and then write the conclusion at the end. Oops. Move that back. All right. So these are our premises, and this is our conclusion Q. Okay, so our premises are P implies Q, and also P, and has a conclusion of Q. And this makes sense to us, right? If we assume that it's true that P implies Q, and we assume that the hypothesis P is true, the only way that an if-then statement can be true when it has the true hypothesis is if the conclusion is also true. So we can conclude that Q must also be true. This argument is called modus ponens, and we can kind of reason to ourselves why this is true, but we can also see in a truth table why it's true. So I set up the truth table for all of these statements here. Now, right, remember, by the definition of a valid argument, it says it has to be the case that whenever the hypotheses are true, the premises are true, in this case, whenever both P implies Q and P are true. So that's going to occur, the only time they're both true is in this first row here, right? In all of the other rows, at least one of those is false. In order for this to be a valid argument, the conclusion must also be true. So our conclusion Q is here, and yes, we can see that it's true. So because whenever all of the premises are true, the conclusion is also true, that's how we determine that this is a valid argument. So we can use these valid arguments to make actual more meaningful statements. So let's give an example of that. Let's look at the argument that all dogs have 4 legs and Spot is a dog. Well, according to modus ponens, this should allow us to conclude that, well, let's think about why modus ponens applies here. So the first statement, all dogs have 4 legs, is a statement of the form P implies Q, right? If something is a dog, then it has 4 legs. The next statement is sort of a statement of the form P because it's saying Spot is a dog, right? Spot is satisfying the hypothesis of that conditional statement. Therefore, we can conclude Q. In other words, we can conclude that Spot has 4 legs. Right, this is what we conclude. The Spot has 4 legs. All right. And because modus ponens is a valid argument, this argument is valid as well. Now, something to keep in mind is that just because an argument is valid doesn't necessarily mean that it's sound. So there's a difference between a valid argument and a sound argument. When we talk about a valid argument, that just means that as long as the hypotheses are true, the conclusion must also be true. For a sound argument, we also require that the premises are actually true statements. And that's not necessarily the case here. So, right, a valid argument is only sound if the premises are necessarily true. That's not the case here, right? I mean, I know that I am familiar with dogs that have 3 legs. If you watch Parks and Recreation, maybe, you know Champion is a 3-legged dog. There's lots of 3-legged dogs. So the hypotheses here are not true statements, but it does follow, it's still a valid argument to say that as long as those first 2 statements are true, we can conclude that Spot has 4 legs. All right, so there's a difference between a valid argument and a sound argument. Let's look at a few more valid arguments. Another common one we have here is called modus tollens. This is an argument of the form, if P implies Q and the negation of Q, in other words, if P implies Q and Q is false, well, then we know that P has to be false, right? So the conclusion here would be not P. This might seem familiar, right? If we're saying that P implies Q and that Q is false, P has to be false as well. This is sort of similar to when we said that a conditional statement of the form P implies Q is logically equivalent to not Q implies not P, right? This is that contrapositive rule that we had seen in a previous section. So this is really just saying, right, if you know that P implies Q and you know that the conclusion is false, well, there's no way the hypothesis could be true here, because then you would have a true hypothesis and a false conclusion, which would tell you that the entire statement is false. So we would have to conclude that the negation of P is true. In other words, that P itself is false. And again, we can check on the truth table that whenever both of the hypotheses are true, or whenever both the premises are true, P implies Q and the negation of Q, we get that the negation of P, right, the conclusion statement is true as well. So we see that this is a valid argument using the truth table. All right, so I'm going to give a bunch of examples of other laws of inference. So modus ponens and modus tollens are a couple examples of laws of inference. I'll give a few more, and I'll leave it to you to check using the truth tables that these in fact are valid arguments. The first is called disjunctive syllogism. It says that if you know that P or Q is a true statement, and you know the negation of P is a true statement, in other words, if you know that P or Q is true, and you know that P is false, well, in order for that or statement to be true, at least one of them needs to be true, and it's not P, so it would have to be Q. So you can conclude Q here. You can check the truth table to see that that's correct. Our next statement, sorry, move this whole thing down. Oh my goodness, sorry. Oh boy. Okay, here, we'll try this again. Our next one is hypothetical syllogism. It says that if P implies Q is true and Q implies R is true, then we should be able to conclude that P implies R. Right? If P being true necessitates that Q is true, and Q being true necessitates that R is true, then following this logic down the line, we get that if P is true, then R must be true as well. All right, a few more. First, let's try to make some space because I know that this is going to get a little bit messed up. All right, so we got 3 more. So if we know that P is true, and we know that Q is true, the conjunction rule tells us that P and Q is true. This is a very simple one to show with the truth table. And the flip side of that is that if you know that P and Q is a true statement, you can conclude P is true. This is equivalent to another law of inference, which says if P and Q is true, you can conclude that Q is true. And finally, the addition rule tells us that if you know P is true, then you know that P or Q is true. Similarly, if you know that Q is true, you know that P or Q is true as well. So all of these are easy enough to check using truth tables. So let's look at one more example of how this works out in practice using an actual meaningful statement. Consider the following. We have a statement that all squares are rectangles. That's true. If a shape is a square, then it's a rectangle. And we have the statement that all rectangles are parallelograms. Yes, this is true as well. It's a statement of the form, if a shape is a rectangle, then it is a parallelogram. This allows us to conclude that all squares are parallelograms. So to see why, right, keep in mind that this first statement is of the form P implies Q. The second statement then would be of the form Q implies R, right, where P is a statement that something is a square, Q is a statement that something is a rectangle, and R is a statement that something is a parallelogram. These are not, I'm using shorthand here, right? These square, rectangle, and parallelogram are just words, they're not statements yet, right? But shorthand to say something is a square, something is a rectangle. And we're concluding in this case that all squares are parallelograms. So we're concluding P implies R. If you look back at our rules on the previous pages, you see that this is an example of using the hypothetical syllogism argument. That's the one where we can sort of put together, am I spelling that right? I think I have to try it again with an I. Hypothetical syllogism argument. It says that if you have P implies Q and Q implies R, then we can conclude that P implies R. All right, that's it for this video.